Okay, fine. So, welcome back again for another class for CRE, Chemical Reaction Engineering for Chemical Engineering Gate. So, last class, let's see, let's just recap for a bit. So, last class, we were looking into, multiple reactor systems. So, yeah, we looked into the multiple reactor systems like series reactors and reactors in series and reactors in parallel and so on. So, we looked at CSTR, PFR in series and parallel, and we tried to see how we can derive equations for such systems, the series and parallel systems. And we also saw that when it comes to CSTR in series, you know an infinite number of CSTRs in series is equivalent to a PFR, and this graph basically shows that. And yeah, we also looked into what will be a better choice when the reaction order is greater than zero. So for reaction order greater than zero, so PFR will be better compared to CSTR in series, and the least favored one is CSTR. And when it is less than zero, the reverse order is true. And for a zero order reaction, PFR and CSTR in series and CSTR all of the above are pretty much same. That means they give the same conversion for the same volume. And yeah, then we looked into PFR in series. And yeah, so today also we'll continue this trend. Okay. 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 So we'll continue with this trend. And so today, what we'll be looking into is, combination of reactors. Then we'll also look into some things like, selectivity and yield. And then we'll also try to look into some complex reactions. Okay, fine. So we learned how we can utilize reactors in series, right? So we can put CSTR and PFR, all these reactors in series and parallel, and we saw that if we keep 2 or 3 CSTRs in series or parallel, how the final conversion will become and so on. But what if we use a combination of reactors? For example, CSTR followed by a PFR, or a PFR followed by CSTR, and so on. So that is what we'll look into here. So I'll just give you the overall outlook for this first, and like we'll be solving a problem based on this as well. So that should give you a complete picture of the things. So basically, when you say CSTR in or a combination of reactors, it usually means a series connection. So you have CA0 here, and you have tau1 here, and this is a CSTR, and this goes into a PFR. So let's say this is CA1, which is the outlet concentration of the CSTR, and then this will be tau2, which is the space-time of PFR, and the outlet concentration, let it be CAF. So the reverse is also possible, like the first CSTR can come, then it is followed by a I mean, first PFR can come, then it can be followed by a CSTR and so on. So the general thing for combination of reactors is that, let's say I'll just write it down here for you. So for reaction orders, this is basically n, that is greater than 1. First use PFR, then use CSTR. So what I am trying to say is, so let's say a question is asked and you have a reaction, let's say something like A gives B, and the reaction is a first order reaction, or let's say B plus C, and the reaction is a second order reaction, KCACB. So in such cases, or you can also have a reaction like this: A gives 2B, and the reaction rate is KCA square. Okay, so in such reactions where the reaction order is greater than 1, and if you want to find what combination gives you the maximum conversion, so let's say you have options, you can use PFR and CSTR in any order, but you have to use it in that order which gives you the maximum conversion. So for that, what we have to do is we have to first use PFR, then it should be followed by CSTR. Okay, so that is what I am trying to say here. So if your reaction order n is greater than 1, first a PFR should come, and this should be followed by a CSTR. And this will give you the maximum conversion for reactions of order greater than 1. Now the same thing is in reverse order when the reaction order for n less than 1. In such cases, CSTR should be used first, followed by PFR. So you first use a CSTR, and the outlet of this can be connected to a PFR. So this arrangement will give you the maximum conversion for reactions having order less than 1. Now the third case is, the obvious one, the order 1, n is equal to 1. In this case, the order doesn't matter. Means you can use CSTR first or PFR first, and no matter what the order you choose, the conversion will remain the same. So this is a general outlook of combination of reactors for various types of reactions. So for order less greater than 1, we have to use PFR first, and that should be followed by CSTR to maximize your conversion. And when the order is less than 1, you have to use CSTR first, that should be followed by PFR to maximize conversion. And when the order is equal to 1, there is no need to follow any order. Whatever order you follow, the conversion will remain the same. So what this means is, so what this means basically is, whether you follow this order or this order, the conversion will remain the same. So that is for order equal to 1. Now there is a special case here. So The special case comes for autocatalytic reactions. So I hope you guys can recollect what you mean by autocatalytic reactions. Can anyone just mention an example for an autocatalytic reaction, like a very simple example? I hope you guys have learned autocatalytic reactions. I think we even discussed about this in class, right? Any volunteers? Yeah. So the product basically acts like catalyst for the more production of the products. So a simple example for this would be A plus R gives R plus R. So basically R is the product here, but the final reaction rate here also depends on the concentration of A. Sorry. So the reaction rate depends on both the concentration of A as well as R. So such reactions are called autocatalytic reactions. Okay, and we also looked at some, derivations and all that, I think. But anyways, long story short, so you'll have an equation for rate of the reaction for autocatalytic reactions. You can plot this equation graphically for autocatalytic reactions. You'll have a graph something like this. That and the graph is between minus 1 by Ra. Sorry. By minus Ra, and this one will be Ca. So the plot will be between the inverse of the rate of reaction and the concentration of A. So now two things you need to remember. The same plot for CSTR as well as PFR. So let's take this is the plot for CSTR and this is the plot for PFR. Okay. So you have a plot like this. For CSTR, we learned that the volume of the CSTR is basically the area like this. Right? This area of this box is basically the volume. Yeah. So this area enclosing this or the box that encloses the curve is the volume of the CSTR. And when it comes to PFR, the area under the curve is the volume of the PFR. Okay, so now if you apply these two things to an autocatalytic reaction, what comes here is the first. So let's say this is an autocatalytic reaction. The order is greater than 1. Okay. Generally, for autocatalytic reactions, the order is greater than 1 because see here A plus R gives R plus R. The reaction rate for this elementary step will be K Ca Cr. Right. So here the order is basically 2. So now we'll use the same graphical procedure and see how an autocatalytic reaction differs from a normal second order or third order reaction. So here, to minimize the volume, what you can do is Now, yeah. So can someone just say we just learned what is the order of CSTR and PFR combination that we use for order greater than one? So what reaction do we use first, and what reactor do we use second? We just learned it in the last 5 minutes. So for second order reaction, will PFR come first or CSTR come first? For a normal second order reaction. Um, can Harshal, Sukeshni? Okay. Yeah. So for a normal second order reaction or any higher order reactions, PFR should come first and it should be followed by CSTR. Now we'll do that same here for this autocatalytic thing, and I'll show you what is the difference here. So this is the normal plot for autocatalytic reaction. Now we just learned that the order is greater than 1. So first PFR should come, right? So let's say PFR covers from this point to this point. Wait, let me just, yeah. So PFR covers from this point to this point. So and then the remaining from here to here, CSTR covers. So this is PFR and this will be CSTR. The first half of the reaction is done in PFR and the second half is done in CSTR. Let's see how the volume will be for this case. Okay, so first case, the volume under PFR, this will be our volume, right? Now, in the case of CSTR, the volume will be like this. Now, this is according to what we just learned, PFR followed by CSTR. Now, I'll show you another case here, the same autocatalytic reaction. If we just reverse the order, okay. Now here instead of using PFR first, we'll use CSTR first. It is followed by PFR. So first is CSTR. So let's say from here to here, CSTR takes over, and from here to here, PFR takes over. Okay. Now, according to the design equation, the area which represents the volume of CSTR is basically like this. You understand? And when it comes to PFR, the area under the curve will be like this. Now, did you understand how we took the area of PFR like CSTR here like this? Because let's say this is CA1, this is CA0, and this is CA2. So this point is called as the operating point of a CSTR. Like a normal CSTR graph, we'll take this endpoint and then we'll find the area like this. And if the reaction curve is like this, the same we'll do there also. We'll take this endpoint and we'll take the area like this. Okay, so basically that is what we did here. Now in these two cases, Just look and see which case gives you the least area. Yes, exactly. So even though your order is 2, that is basically your order is greater than 1, instead of using PFR first, if we use CSTR and then we use PFR, it will be giving you a better conversion for a given volume, or lesser volume for a given conversion for autocatalytic reactions. So basically, the case for autocatalytic reactions is reversed to that of a normal higher order reaction. Okay, so that is what I am trying to explain it to you guys graphically. Okay, fine. So that's about it for a combination of reactors. Now we'll look into some more stuff with regards to multiple reactions. So let's take parallel reactions. So let us say we have a reaction like this. Parallel reaction, A gives R and A gives S. And the rate minus RA will be K1 CA raised to N. Now this is rate of formation of R, and this is RS, and that will be K2 CA raised to M. Now the term selectivity. Have we learned selectivity before? No, right? Okay. So basically selectivity, this means selectivity upon, one second. Yeah. Selectivity of R upon S. This will be basically rate of reaction of formation of R by rate of formation of S. So in general, selectivity of anything is basically rate of desired reaction by rate of undesired reaction. So when we say selectivity of R upon S, that means for this particular scenario, R is the desired product. Okay. And S is the undecided product. Now, if the situation was reversed, selectivity of S upon R, that means S is our desired product instead of R, then the selectivity, selectivity of S upon R will be RS by RR basically. In this case, S is our desired product. So basically in general, selectivity means, rate of desired reaction by rate of undesired reaction. Okay, so that is what selectivity means. And then the next term is yield. So same thing, let's say A gives R and A gives S with RR as K1 CA raised to N and RS as K2 CA raised to M. So yield is basically rate of desired reaction by rate of desired reaction by total rate of reaction. Okay, so let's say yield of R, then this will be rate of formation of R, that means RR by rate of total rate of reaction, that means minus R, and this minus RA is nothing but RR plus RS for a parallel reaction. I hope you guys understood how this was arranged, because minus RA is basically K1 Ca raised to N plus K2 Ca raised to M, and this K1 Ca raised to N is RR and K2 Ca raised to M is RS. So minus RA is equal to, so basically yield of R will be RR by RR plus RS, and yield of S will be RS by RA, and that will be RS by RR plus RS. Okay, so this is the definition of overall yield of a product from a reaction. Okay, so any doubts on this so far? Okay, so yeah, now let's look at one more thing: complex reactions. Now let's say if we have a reaction like this. Yeah. Just a second. Yeah, okay. So let's say we have a reaction, A gives R and S, and this R gives T. This gives U. So these kinds of reactions, or we can have something like this: A gives, reversibly gives B, this reversibly gives C. So these kinds of reactions are basically called as complex reaction. So this is a cyclic reaction. So this will be K1 K minus 1, this will be K2 K minus 2, and K3 K minus 3. So this will be K1 here, K2 here, K3, K4. Okay, so yeah, for cyclic reactions I think we learned one thing: the product of equilibrium constants. So equilibrium constants here will be capital K1, that will be small k1 by k minus 1, then capital K2, this will be K2 by k minus 2, and K3, this will be small k3 by k minus 3. So these are called as equilibrium constant. So equilibrium constant is basically the reaction rate constant of the forward reaction by reaction rate constant of the backward reaction. And for cyclic reversible reactions, we learned this thing: the product of equilibrium constants K1, K2, K3 will be equal to 1. Okay, and for now we'll simplify this a bit. So we'll just take something like A gives R S. So basically what this means is this is K1 and this is K2. Basically, you can rewrite this reaction as A gives R plus S, right? And let's take this as K3. So what will be K3? K3 will be basically K1 plus K2. Okay. So I just wanted to mention this thing before we moved on. Anything else? Yeah, I think that's about it. Yeah. K4, K1, K2. Okay, fine. So yeah, I just wanted to mention this bit before we moved on to the problems. So, any doubts so far regarding this complex reactions or combination of reactors or anything? So when that combination of reactors, as I said, we'll solve a problem based on that, and you'll get to see why for first order reaction the order of the combination of the reactors doesn't matter and so on. Okay. So if there are no doubts, we'll move into the questions. Fine. So let's move on. I hope. Okay. So this is a question from GATE 2015, Chemical Engineering, GATE question number 56. So consider two isothermal flow configurations shown schematically as case 1 and case 2 below. In case 1, a CSTR of volume V1 is followed by a PFR of volume V2, while in case 2, a PFR of volume V2 is followed by a CSTR of volume V1. In each case, a volumetric flow rate of liquid reactant is flowing through the two units in series. An irreversible reaction A gives product of order N takes place in both the cases with a reaction concentration Ca0 being fed into the first unit. So these are the two cases given. We have to choose the correct option for this. So option A, so we have to choose the correct options from these four options. So option A will be Ca final of case 1 by Ca final of case 2 greater than 1 for n equal to 1. Option B, Ca final case 1 by Ca final case 2 is equal to 1 for n is equal to 1. Option C, Ca final 1 by Ca final 2 less than 1 for n equal to 1. And option D, Ca final 1 by Ca final 2 is equal to 1 for n greater than 0. So this is a question from combination of reactors from chemical reaction engineering, and the reference NPTEL series can be found in module 1, lecture 26, reaction design for mixed flow reactors and combination of reactors, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So to do this problem, let's see how we can proceed with this. So let us take a reaction like this. A gives B, and the order of this reaction, let that be 1. And the reaction rate will be given by minus Ra is equal to Kca. So let us take case 1. So in case 1, it is CSTR followed by PFR. So let us take a CSTR, and this is followed by PFR. Let us take the entry point as Ca0 and Q0 or Q, whatever. Then Ca1, and the final outlet concentration is CaF. Alright. And let tau1 be the spacetime of CSTR and tau2 be the spacetime of PFR. So obviously V1 will be the volume of CSTR and V2 will be the volume of PFR. So now tau1 can be written as V1 by Q, which will be equal to Ca0 minus Ca1 by KCA1. That is basically, this is the design equation of the CSTR. Now, if we write the design equation of PFR, it will be tau2 will be equal to integral of Ca1 to Ca2 minus dCA by minus Ra, and minus Ra will be KCA. Right. So this will be design equation of PFR. So now let us try to simplify these two. So here what we need to do is, we'll take a balance, component balance. No, we don't need to take a component balance here. We can just rewrite the yeah. So let us take this as equation 1 and this as equation 2. Okay. So now from equation 1 we have V1 by Q is equal to Ca0 minus Ca1 by KCA1. Right. So we can just rewrite this. So V1 KCA1 will be Q into Ca0 minus Q into Ca1. Okay. And from this we can write Ca1 will be equal to Q Ca0 by V1K plus Q. So this will be the equation of Ca1, which is the intermediate concentration here. So we can even simplify this a bit more. So let's say we divide this whole thing, numerator and denominator, by Q. So this can be written as Ca0 by V1 by Q into K plus 1. And what is this V1 by Q? That is basically tau1, right? So Ca1 will become Ca0 by tau K plus 1. Right. Now we go for equation 2 with respect to PFR. So for PFR we wrote that tau2 is equal to integral of Ca1 to CaF minus dCA by KCA. If we integrate this, basically it will be 1 by K ln Ca from limit Ca1 to CaF minus 1 by K. And so tau2 will be basically 1 by K ln Ca1 by CaF. Now if we take this K to this left hand side, it will be tau2 K will be ln Ca1 by CAF. And from this CAF will be, we have to find this CAF. We can find that by taking the exponential from both sides. So taking exponential of tau to k will be basically CA1 by CAF. So that means CAF will be CA1 e raised to minus tau to k. So this will be CAF, and we also have the CA1. So CA1 is the concentration of A after PFR, and this will be the final concentration of A. Okay, so this is the final concentration of A after the PFR. So we have the equation for CA1 here. We just substitute that CA1 equation in this CAF. So CAF will be equal to CA0 by tau k plus 1 e raised to minus tau 2 k, tau 1 k. Yeah. So this is the final concentration of A after passing through the CSTR and then the PFR. Right. Now let us look at the next case, case 2. Now in case 2, first PFR will come and then that will be followed by CSTR. Now previously we took tau 1 for CSTR and tau 2 for PFR. So we will follow the same nomenclature here to avoid confusion. So tau 2 will be the spacetime of PFR and tau 1 will be the spacetime of CSTR, and consequently V2 and V1 will be the volumes of PFR and CSTR respectively. Now this will be the entry at PFR will be CA0, CA1 will be the final concentration after the exit at PFR, and CAF will be the final concentration after this whole combination of PFR and CSTR. Now what we'll do is we have to find this CAF here, and let us see how we can find that. So writing the design equation for the PFR first, because PFR comes first. So we write the design equation of PFR, that will be basically tau 2 is equal to integral of CA0 to CA1 minus DCA by minus RA, and that will be integral CA0 to CA1 minus DCA by KCA. So this is basically minus 1 by K ln CA from CA0 to CA1, and we can write this as 1 by K ln CA0 by CA1. So tau 2 is equal to 1 by K ln CA0 by CA1. We can rearrange this a bit. This will be tau 2K will be ln CA0 by CA1. If we take the exponentials, it will be e raised to tau 2K, that is equal to CA0 by CA1, and that means CA1 will be CA0 into e raised to minus tau 2K. Right. Now if we take the case of design equation, so this is the design equation for PFR. Now we do the same for CSTR. For CSTR, tau 1 will be CA1 minus CAF by K CAF. Now rearrange this. Tau 1 K CAF is equal to CA1 minus CAF, and tau 1 is basically V1 by Q. So V1 by Q K CAF is equal to CA1 minus CAF. Now all we have to do is rearrange this. Yeah. Okay. So if we rearrange that equation to find CAF, so CAF will be CA1 by tau K plus 1. Okay. Now from here we have CA1. So we substitute that CA1, that will be, yeah. So CAF is equal to CA0 into e raised to minus tau 2k by tau 1k plus 1. So this is the final concentration of A after the combination in case 2. Okay, so now let us just write the final concentrations of case 1 and case 2 together. So for case 1, yeah, so this is case 1. So for case 1, we can see CAF. So we will write it as CAF case 1 is equal to CA0 by tau 1k plus 1 e raised to minus tau 2k. And for case 2 also, CAF is equal to CA0 by tau 1k plus 1 e raised to minus tau 2k. So from this CA1 and CAF2, we can see that both these are same. So that means for order n is equal to 1, CAF case 1 by CAF case 2 is equal to 1. Okay, so out of these 4 options, the right option here is option B. So basically what this means is, for order having a reaction, for reaction having an order 1, whether we put CSTR first or PFR first, the combination of these reactors will always give you the same outlet concentration as well. So for case 1 as well as case 2, the final concentration CAF will basically be same. So the right answer here is option B, CAF case 1 by CAF case 2 is equal to 1 for order n is equal to 1. Okay, so yeah, CA1 is equal to CA0 by, yeah, so that one I'll show it. That is right. So CA1 is equal to Ca0 by e raised to tau 2k, right? Yeah, it's fine, it's fine. Yeah, basically if we take this on top, it will be Ca1 is equal to Ca0 e raised to minus tau 2k. That's all. Fine. So is this question clear? Like you understood what we were doing, right? So basically what we are doing is just finding the final outlet concentration for both these cases. So for case 1 as well as case 2, we are just finding the outlet concentrations and we are proving that they are equal. And that is why for first order reaction, no matter what order of the combination of reactors you follow, the final outlet concentration will remain the same. Okay, fine. Shall we look into one more question? It's kind of a straightforward question. Okay, fine. So this is a question from Chemical Engineering Gate 2015, question number 59. An isothermal steady state mixed flow reactor or CSCR of 1 meter cube volume is used to carry out the first order liquid phase reaction A gives product. Fresh feed at volumetric flow rate of Q containing reactant A at concentration Ca0 mixes with the recycled stream at a volumetric flow rate of Rq as shown in the figure below. It is observed that when the recycle ratio R is equal to 0.5, the exit conversion XAF is equal to 50%. When the recycle ratio is increased to R is equal to 2, then the new exit conversion in percent will be option A 50%, option B 54.3, option C 58.7, and option D 63.2. So this is a question from recycle reactors from chemical reaction engineering, and the reference NPTEL series can be found in module 1, lecture 26, reactor design for MFR and combination of reactors, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here they have given us a CSTR with recycle. So as you can see in this picture, we have an initial flow rate of 0.5 meter cube per minute and initial concentration of 1 mole per meter cube, and this enters as CSTR, and the final concentration will be CAF with the final conversion as XAF. And the recycle stream is also given as RQ. That means the recycle ratio is basically R. And they have said that when the recycle ratio R is equal to 0.5, the exit conversion is 50%. That means this XAF will become 50% for R is equal to 0.5. Then when R will be increased to 2, what will be the exit conversion? That is what they have asked us to find. So let us see how we can proceed for this. So let us take two cases. So case 1, CSTR with no recycle. Okay. So let us take a CSTR like this. Now Ca0 as our initial concentration, Q will be our flow rate, and let's say tau is our space time with V as our volume, and CAF will be our final concentration. Okay. So let us take the reaction as A gives B just to keep things simple, and it is a first order reaction, and the reaction rate is equal to KCA. So for this, if we write the design equation, it will be tau is equal to V by Q, and that will be equal to Ca0 minus CAF by KCAF. You can also write this as Ca0 into XAF by KCAF. Okay. Now we can write the CAF as Ca0 into 1 minus XAF. Right. So just rewrite this equation for tau. Tau will be Ca0 XAF by K into Ca0 into 1 minus XAF. So Ca0 get cancelled. If we take this K from the right hand side to the left hand side, it will be tau K is equal to XAF by 1 minus XAF. And if we rearrange this a bit more, we can get XAF is equal to tau K by 1 plus tau K. So this is the final conversion without recycle. Okay. Now let us take the next case, case 2, as CSTR with recycle. So we'll draw a simple schematic here. So we have a CSTR like this. This is our inlet concentration Ca0. This is our outlet CAF, and let this be our recycle stream. Now the recycle ratio will be R, and this flow rate here will be R into Q. So Q is the flow rate initially, and again we'll take tau and V as our space-time and volume of our reactor. Right? The flow rate here also will be Q. So one more thing we need to know, that the concentration at the inlet now has changed because of this recycle. So the concentration at the inlet of the CSTR will be Ca1, and the flow rate at the inlet of the CSTR will be Q1. So we have two new terms here, Ca1 and Q1. So let us see how we can find these two new terms with respect to the known values. So the design equation basically says tau is equal to V by Q1. Now this is not V by Q, this is V by Q1, and that will be equal to Ca1 minus CAF by KCAF. Notice the difference here. So in the previous case with no recycle, the design equation was tau is equal to Ca0 minus CAF by KCAF. Here, because of this recycle, the concentration and the flow rate at the inlet has changed, and now the design equation for this CSTR will become V by Q1, which is equal to tau, that is equal to Ca1 minus CAF by KCAF. Right. Now let us take a flow rate balance throughout the system or at the entry point. So basically this part. So this was Q, this was RQ, and this became Q1. So we are talking about this entry point. So if we write the balance, Q1 will be equal to Q plus RQ, right? Or basically Q1 is equal to Q into R plus 1. So out of these two unknowns, now we found out Q1 in terms of our initial flow rate Q. Now we need to find CA1. So for CA1, what we'll do is we'll write the component balance of A at entry point. So here it was CA0, here it was CAF, and here it is CA1. So if we write the component balance, CA0 into Q plus CAF into RQ is equal to CA1 into Q1. So basically this is just in minus out is equal to 0 kind of balance. So if we rearrange this a bit, we can write CA0Q plus CAF RQ will be equal to CA1, and we just found out the value for Q1. Q1 is Q into R plus 1. So just substitute it there. It will be Q into R plus 1. So from this equation, this Q will get cancelled from all these terms, and final will become CA0 plus CAF is equal to CA1 into R plus 1. Now from this we can write CA1 as CA0 into, sorry, there is an R here. Yeah. So the equation will become CA0 plus CAF into R is equal to CA1 into R plus 1. Now we can write CA1 as CA0 plus RCAF by R plus 1. Okay. So now we have the concentration CA1 and the flow rate Q1 at the entry point, right? So we'll come back again to the design equation of CSTR with recycle. So that design equation was basically tau is equal to V by Q1 is equal to CA1 minus CAF by KCAF, right? Now what we'll do is substitute Q1 and CA1 in the design equation. Okay, so V by Q1 is basically Q into R plus 1, and that will become CA1, and CA1 we just found out here, that will be CA0 plus RCAF by R plus 1 minus CAF the whole by KCAF. Let us try to simplify this. So V by Q into R plus 1 is equal to, if you take the LCM and do some rearrangement, it will be CA0 plus RCAF minus RCAF minus CAF, the whole by R plus 1 into KCAF. Now this RCAF and RCAF will get cancelled. This R plus 1 on the right hand side and R plus 1 on the left hand side will also get cancelled. And we'll get a final equation V by Q is equal to CA0 minus CAF by KCAF. And this is equal to tau. So this is the tau for CSTR with recycle. Now if we look carefully, the tau for CSTR with recycle is basically equal to the tau for CSTR without recycle, right? So basically what this means is, if we try to find the conversion here, so for CSTR with recycle, tau is equal to CA0 minus CAF by KCAF, and that is CA0 into XAF by K into CA0 into 1 minus XAF. CA0 get cancelled. Tau K will be XAF by 1 minus XAF, and XAF will be tau K by 1 plus tau K. So this is same, the conversion for CSTR with recycle is same as the conversion of CSTR without recycle, right? So basically what this means is, recycle has no effect on the conversion of CSTR. So this is the important takeaway from this whole numerical manipulation that we did. So what this basically means is, whether R is equal to 0.5 or R is equal to 2, whether the recycle ratio is 0.5 or it is 2, the conversion remains unaffected. That means the conversion will remain at 50%. So no matter how much the recycle ratio is manipulated for a CSTR with recycle, the conversion will remain the same as the conversion from a no recycle CSTR, right? So here the right option here is option A, 50%. Okay, so did you guys understand how we did this? Basically what we did was, we just tried to find an equation for the conversion of CSTR with recycle as well as without recycle, and in the end, after doing the manipulation, we found that the conversion for CSTR with and without recycle is anyways the same, right? So the conversion was basically XAF is equal to tau K by 1 plus tau K. So that is pretty much the same equation for CSTR with the recycle as well as without recycle. So that means recirculation or recycle stream has no effect on the conversion of CSTR. So no matter how much the recycle ratio is increased, the conversion will remain the same here. And they have given that the conversion was 50% when recycle ratio R is equal to 0.5. So when recycle ratio is 2 also, the conversion is still going to be 50%. Okay. PFR with recycle will inherently vary. What we'll do is in the next class, we'll start with the equations for PFR with recycle. So actually, what I would suggest you to do is, did you see how we did these balances here? I'll show you it. So these two equations, this Q is equal to Q into R plus 1, as well as this equation. Sorry, here. This CA1 is equal to CA0 plus RCAF by R plus 1. This will be same for both CSTR as well as PFR. So for PFR, what will vary here is when you substitute it like this, there will be an integral. So I'll show you it. So for PFR, tau is basically integral of dCA by kCA, right? And this will be from CA1 to CAF. So I'll just draw. So this will be CA0, the entry will be CA1, this will be Q0, let's say, and this will be Q1. This will be R into Q0. This is CAF. This will also be CAF. This will be Q0. Right? So this tau will be V by Q1. So here also Q1 is basically Q0 into R plus 1. And CA1 will be, just like this. If we take the component balance at the entry, like what we did here for, our CSTR with recycle. So what we did here, we just took the component balance at the entry point like this. We can do the same thing there also, and we'll get the same equation. This CA1 is equal to CA0 plus RCAF by R plus 1. The same equation we'll get here also. So it will be CA0 plus RCAF by R plus 1. Now the difference here is, then our equation will become V by Q1, which is basically Q0 into R plus 1, and that will be equal to integral of minus dCA by kCA, and CA1 will now be CA0 plus RCAF by R plus 1, and the final concentration CAF. So this will be the equation for design equation for a PFR with recycle. You get it? So basically what we need to do here is do a balance at entry point to find this both CA1 as well as Q1, and if we have those two values, then everything else is just the basic design equation. You just write the design equation and substitute for CA1 and Q1. Right? Did you is it okay? Is it understandable? Okay. So now the difference here for PFR is you basically have to integrate this integral dCA by kCA, and when you apply the limits, you can, if you know the value of CA1, you can apply the value of CA1 and do the integration. If you don't know the value of CA1, you have to find the value of CA1 using this equation CA0 plus RCAF by R plus 1, and then you do the integration. That's all. So once you just use for recycle reactors, whether it is CSTR or PFR, all you need to find is the new flow rate Q1 and the new inlet concentration Ca1. So once you find these two values, it is pretty much the straightforward method for you know solving these problems. So is this clear? Okay, fine. So we'll stop here for today, and yeah, next class. Let's see. So now that I just explained the recycled PFR, so I don't think we need to explain it again, right? If you have any doubts, of course, just let me know during next class, and we'll go through this recycled PFR once more. But if not, we'll start with some new topics, and let's see, how it goes. Fine. Okay. So yeah, that's it for today, and thank you for joining, and I'll see you guys next Monday.